Hello and thank you all for joining us in Earmarks webinar series. Today webinar will cover performance calculation of a three-phase transformer under both no-load and on-load conditions. Okay, let's see our agenda for today's webinar. So we will be starting by listing the design challenges of three-phase transformers. Then we will see Earmarks' proposed solution to solve and overcome these challenges. A section of simulation and results will be covered. Transformer Wizard, which is a CAD design tool for transformer application, will be demonstrated. And before ending this webinar with a QA session, we will have a live demonstration. So as you know, three-phase power transformers have a prime position in energy distribution networks and in power systems. These systems require efficient distribution capacity and high power transmission capabilities. As crucial components in electrical grids, transformers are built to the highest standards of precision and quality and designed to be efficient for a long operation time. So as a result, designing a transformer is important and necessary to develop reliable systems. And this step requires solving several issues and perform various tests and analysis. And these tests can be performed through computer simulation software to save time and money. Some of the design issues posed by power transformers and can be addressed through computer simulation are steady state and transient magnetic analysis. So the magnetic fields needs to be calculated or investigated, and the saturation level needs to be evaluated as well. Trying different winding configuration and connections like delta and star connections and explore their different impacts. AC and DC resistances and inductances of the transformer windings need to be evaluated as well. So performing or studying the transformer under no-load analysis is mandatory to extract the equivalent circuit of the transformer and also investigate the high current levels in case of short circuit. So this will should be done before building the transformer to evaluate the short circuit current and the risk of damaging the whole system or the whole power system because of these currents. Also, the core shape and its design can be investigated and improved. The impact of using different steel also need to be explored. Losses as well are important to determine the efficiency of the transformer, so they have to be accurately estimated, so mainly to reduce the heat in the transformer. Also, predicting the temperature and structural deformation are important in transformer design. So while designing a transformer, temperature and deformation in the structure have to be evaluated. Finally, insulation failures have to be investigated to limit the breakdown voltages. So in case we have like high voltage, so there might be some breakdown voltages. So this is why we need some investigation of electric field, and we need electric field analysis for this reason. Alright, so adopting an accurate and a complete solution helps to overcome those issues during the design process of a power transformer. EMWorks proposes a solution for transformer application, which is an electromagnetic simulation package that covers both 2D and 3D problems. So 2D problems are used at the beginning and at the middle stage of the design process, because 2D analysis runs faster and we can solve more iterations in less time, while the 3D analysis is used usually at the end or at the end stage of the design process to validate the final results, because 3D simulation can take into account most of the 3D related physical phenomena. Yeah, so and also whether you have like planar or rotational symmetry, so 2D analysis can cover both cases. Yeah, various results are computed using this solution, like magnetic fields, current, voltage, losses, coil parameters, and so on. Moreover, this solution came with an integrated circuit simulator. So we have a circuit simulator that can be used to model circuits there. So you can model your transformer using some components. We have linear and non-linear components like resistors, resistances, inductors, capacitances, diodes, switches. So all of these electronic components can be included in your circuit simulation. In addition to this, multi-physics options are available to help designers and engineers with a seamless workflow to calculate the temperature and structural deformation of the transformer. So within your same analysis and same study, so you can solve and get results of magnetic analysis, thermal analysis, and structural analysis. So you can have like 3 coupled analysis within the same study, so without the need to export or import any data. So one single shot you can get through one single shot you can get 3 folders of results. Yeah, so this package or this solution contains also a transformer wizard, which is a template based transformer CAD design, so it is used to automatically generate single phase and 3 phase transformers. So it automatically generates geometry for these transformer applications. So the user has only to put some parameters, some geometrical dimensions and so on to get geometry ready for simulation. And finally, this solution, this package, this full package with all the analysis we listed are integrated inside SolidWorks and Autodesk Inventor, which are powerful and flexible CAD tools. So they allow a lot of geometrical features and options. Yeah, so now let's move to our case study. We will have look at some simulation and results done with this solution. Okay, so this is the model that we are going to solve using both EMWorks2D and EMS. As you can see at the top right figure, we have a 3D model of a 3-phase transformer. This model was simplified using 2D simplification feature of EMWorks2D into a 2D geometry. So 2D simplification is a feature that allows to automatically generate a 2D geometry from a 3D native geometry. So if you have like a 3D geometry, you can simply get a 2D geometry using this 2D simplification without the need to recreate 2D geometry from scratch. So just bring your 3D geometry, whether it is SolidWorks or Inventor native, then or any other CAD tool from any other CAD tool, then use the 2D simplification feature of EMWorks2D to simplify it and extract a 2D geometry without deleting the 3D geometry. So you will have both 2D and 3D geometry within the same model. Okay, so EMWorks2D is the 2D simulation software of EMWorks solution, and EMS is the 3D simulation software. So EMWorks2D for 2D analysis, EMS is for 3D analysis. Alright, so the design details, we have a 3-phase transformer. The frequency, the operating frequency is 50 Hertz. Primary winding are turns are 100. We have 1100 turns in the secondary side, and 2 type of connections will be performed in this for these analysis. So we have star-star connection and delta-star connection. Okay, so these are the connections that I mean Y connection here is shown, and delta connection is also shown. So as you can see at the top figure, so we will be starting our simulation using a Y connection in both sides, primary and secondary side of the transformer. So transient magnetic solution using EMWorks2D. So this is our first analysis. Open circuit analysis is performed. As you can see at the left side, we have a circuit modeled inside the software using EMWorks2D circuit simulator. So using the circuit simulator of EMWorks2D, we created this circuit. So as you can see at the primary side, we have three sources of voltage, and we have three windings. Then we have three windings at the secondary side, and they are not connected, so it's an open circuit here. So the input voltage is 1 kilovolt, and the frequency, as mentioned previously, is 50 Hertz. So at the right side we can see an animation of the magnetic field versus time. So the transient simulation means that we have results versus time. So we have all the results quantities are generated versus time. So as you can see, the distribution of the magnetic fields here versus time. Okay, so this helps to identify any saturations in your material. So you can change the material. So we have a wide range of materials in our material library. So you can change the material and investigate the saturation levels of the transformer core. Okay, here we can see some waveforms, induced voltage at no load. So it can be seen here that we have 6 voltages, 3 for primary, 3 for secondary. The right figure contains the different core losses. So we have eddy losses. So they are mainly, or they are exclusively in the core. So we have eddy loss, hysteresis losses, excess losses, and the sum of them, which is the core loss. So you can see the variation of the core loss versus time, and also the voltage versus time. So the core loss model comes with a material definition. So in the material library you can find the core loss data, use it for a specific material. Then the simulation, or during the simulation, the core loss will be computed. Here another type of circuit, which is the short circuit. As you can see, a short circuit performed or created using the circuit simulator of EMWorks2D. So here we performed the short circuit with a reduced voltage to compute the current, the short circuit current. This helps to, investigate and see the short circuit current levels and how they are behaving versus time. So at the right side we see also the magnetic fields varying versus time. Okay. Now the induced voltage versus time and the current versus time. So these are the right figures. The right figure contains the current, the short circuit current versus time. It can be seen that the current is high, reached higher value because of the short circuit test. Okay, so the winding losses for short circuit case are computed. So the total winding losses are computed for all the windings of the transformer, and can be seen in the left figure. So the losses reached like values like around 17 kilowatt, which is high losses, copper losses. At the right side we can see some animation of the winding loss versus phase. So it's the winding or the loss distribution is plotted and animated versus phase or time. A loaded circuit here is used. So we coupled our we connected our secondary part or side of the transformer to a resistive load here, and we used 1 kilowatt as input voltage. Then we run the simulation and get magnetic fluxes and so on. So you can see at the right side the distribution or the animation of the magnetic field versus time. Here some induced voltage versus time as well, so the variation and the evolution of the induced voltage versus time. At the right side we can see the load current, I mean the input current and the load current, the current in the loads, so it is plotted versus time as well. And we still under the YY connection, so both primary and secondary are connected in star. The overall core loss is plotted here under load conditions, so this helps to estimate, I mean, the losses when load is connected to the transformer. So at the right side we can understand different quantities of the losses, so which is, I mean, helpful to estimate which is the most important part of the core loss, whether it is eddy, so whether the losses, the most important or the major part of the losses are coming from eddy or hysteresis loss. Okay, now we are going to study the Y or the delta connection. Here is our primary side is connected in delta, and we can see short circuit analysis under delta star connection. So you can see the animation of the magnetic field. So this allows, I mean, several connection types, so you can perform any connection that you want here and investigate the results. Here we can see some current versus time, short circuit current versus time, and the induced voltage results versus time as well. Winding loss are also evaluated, so you can see here higher winding loss compared to the star connection. So the winding loss reached 50 kilohertz. So we know that in delta connection, so we can get higher current when we use like loaded load connection, but here we have higher losses while under short circuit. So the delta connection can provide more power to our load, but also it can result in higher losses and higher short circuit current in case of short circuit. So this is the disadvantage of this delta connection. Okay, so now we connected our secondary to a load, and we are gonna investigate and see the results. So it can be seen also the distribution of the magnetic flux versus time. Here also some plots of the current versus time and the losses versus time as well. So now we are moving to another section of simulation. So we will see how we can use a 3D analysis and use a steady state magnetic analysis. So instead of the time domain analysis, we are going now to use a harmonic analysis to get the steady state results of transformer, three-phase transformer. So so this can be also done with a 2D, but we switch it to see the 3D analysis. So here we have like a load connected to the secondary side, and we have a delta connection at the primary side. So we can see at the right side the distribution of the full 3D model and the cross-section view of the magnetic flux. So it's versus phase here. So the distribution of the flux versus phase. Winding loss distribution, so you can get the distribution and identify the hotspots in your design. So you can get the winding distribution, core loss distribution, and so on. So as mentioned, so this our solution can allows to couple multiphysics options like thermal. So here we use it AC coupled to thermal. So we use the AC magnetic analysis coupled to thermal to get the temperature under steady state condition. here. So you can see the steady state temperature distribution. We have a higher temperature in one of the primary winding, and also some higher temperature in the core. At the right side, we isolated the core and to identify the distribution of the temperature in the core because of the core losses. Also, with using the same study, we added the structural coupling. So we have now magnetic analysis coupled to thermal and structural. We have 3 analysis types within a same study, and this to get the structural analysis, the structural deformation of the structure for both the core and the winding. So both the structural here, or the deformation in the structure, is caused by both magnetic forces and thermal stress. So we have the deformation of the core caused by the magnetic forces applied to the core, and also the heat generated. The same for the coils. So we can see some deformation in the coils because of the current, the Lorentz forces, and the heat generated because of the ohmic losses. So, but you can also still do structural standalone. So you can do, magnetic analysis coupled to structural alone. So if you don't want to include the thermal in your structural analysis. So we want to get only the structure that is caused by the magnetic forces, any magnetic forces, whether it is caused by ferromagnetic in ferromagnetic parts or conductive parts. Yeah, now we are going to see another kind of analysis, which is the investigation of the dielectric failure. So we modified a little bit our transformer. We added insulation, oil as insulation inside an outer tank. So we have an outer tank made of steel. We have some steel shunts, and we have also the oil, which is added for the insulation. So the 3D model includes this magnetic shunt, oil for insulation, and tank. So we have the dielectric strength is defined for the oil. So it has this high value, and we will perform an electric analysis. So EMS has both electric field analysis and magnetic field analysis. So we have modules for magnetic analysis, and we have modules for electric field analysis. So this is the same for the 2D simulation. So we have comparable modules for both software. We have almost the same modules for 3D analysis and 2D analysis. So as you can see at the left side, animation of the voltage distribution versus applied voltage. So we applied here, we use it. Okay, here we use it a parametric analysis to apply different voltages to our to the transformer windings. So we applied different voltages, and we investigated the dielectric failure versus the applied voltages. How we can do this? So you can first we can see the voltage distribution versus different voltage applied voltages. So in the right side, we see the animation of the electric field versus applied voltage. So we can investigate the field distribution and compare it against the dielectric strength of our insulation material. So if the electric field becomes higher than the dielectric strength, then there is a risk of breakdown there. But this can be also done automatically with the software. So we have a quantity which call it safety factor. So the safety factor is a post-processing quantity that compares the electric field against the dielectric strength of the material. So here the software compares automatically the electric field versus against the dielectric strength of the material. Then it generates a quantity. So a quantity, it call it the safety factor. So if the safety factor is higher than 1, it means that there is a risk of breakdown. So there breakdown voltage. So there might be some dielectric failure there. So it can be seen from the left figure that at the beginning there is no red colors, so when when some red colors appears, it means that there is some breakdown voltage there. So this can help us to identify the dielectric failures of the insulation that we are using in our transformer. Now, yeah, some isoplots are also shown in the right side. So yeah, okay, so here now we will have a quick demonstration of transformer wizard, so which is a CAD design software for transformer application. So it helps to automatically generate both single phase and three phase transformers through template based or templates that are that came with the software. So the user has to specify some geometrical inputs and automatically generate 3D geometry of this the transformer, whether it is single phase or three phase, and also can be these these models can be simplified into two models using the 2D simplification of EMWorks2D. So all the tools are connected to each other, so they can be added or can be used together. Okay, here quick demonstration here. So transformer wizard is integrated inside SolidWorks, so you can choose the 3D model and choose whether you want to generate a single phase or three phase. Then we have properties for core, so you can choose the type of the core that you want to use. Okay, so you browse the core type here. So we have couple of several core types, and you choose one of them. So there is a gapped cores as well. Then you specify, we have some previews, some image for preview. Then you edit some dimensions, or some properties and parameters. Then you validate the core. Then you move to the bobbin and choose the type of the bobbin, the shape, and specify its dimension. So you have diameter, thickness, and so on. Then you validate. In case you enter something that is non-consistent, so the software helps you to identify that and fix it. So yeah, validate, then you generate. If everything is fine, then you can generate your transformer model. So it's automatically, you can see that it's quickly generated. It is, yeah, you can see here cross-section view of the transformer, of the three-phase transformer we generated using transformer wizard. You can edit, so yeah, you can still able to edit and so on. Alright, so now let's try to have a quick look at both EMS and EMWorks2D inside SolidWorks. Let's move to some live demonstrations. Okay, let me switch my presentation. Okay, so now I switch it to SolidWorks. As you can see, this is the model inside SolidWorks. This is the 3D model. We have EMS here, EMS tab, and EMWorks tab inside SolidWorks. So both EMS for 3D electromagnetic analysis and EMWorks2D for 2D electromagnetic analysis are integrated inside SolidWorks. This is, let me go back here to SolidWorks 3, so you can see the 3D model. And if we want to do first a 2D analysis, we can just use, as mentioned during the presentation, the feature of 2D simplification. So you can choose this option and you choose what kind of symmetry that you have, and select, for example, this is somehow a planar symmetry, so we are supposing it has some planar symmetry. Then we will do or generate a 2D model according to this coordinate system. So we will keep surfaces only, the surfaces that only belong to XY plane. here, as you can see. So, and if I hit OK, so it will generate the 2D model. Okay, let me go back to the 3D now. So yeah, EMS. So let me show the type of analysis that it is possible. So we have study, then a property page. In this property page, we can see 6 modules. So magnetostatic, AC magnetic, transient magnetic. So these 3 modules for magnetic analysis. So magnetostatic is for DC electromagnetic analysis, DC magnetic analysis, AC for sinusoidal excitation magnetic analysis, and transient for it's a time domain magnetic analysis. So it can be used for any type of excitation, whether it is sinusoidal or DC or pulse or whatever, or you can even import your excitation from an external file like text or Excel file. So, and we have electrostatic conduction, electric conduction, AC electric for electric field analysis. In addition to these modules, so we have a few multi-physics options. So we have thermal. So the thermal contains 2 options. So you can have steady state thermal or transient thermal. So you can get just the temperature at the steady state temperature, or you can get temperature versus time. You can solve your temperature versus time. We have also structural, motion analysis, and circuit coupling. Circuit coupling means that we can draw our circuit using the circuit simulator that is integrated with the software. So yeah, so these are the multi-physics options. Let me go back here. So parameterization. So we can see this feature. Parameterization allows to parameterize both geometrical and simulation variables. So you can parameterize your geometrical dimensions, distances, angles, and so on. So you can parameterize whatever you want in your geometry. So you can, for example, vary the shape or of the core, for example, and see its impact, vary maybe diameter of the coil, whatever. So you can do that. Also, in addition to this option of parameterization, where you can vary some geometrical dimensions and so on, we have also the ability to use the multi-configuration feature of SolidWorks. So let me just show what is here. So as you can see, this multi-configuration feature of SolidWorks, so you can run couple of designs within the same model. So you want to try, for example, core with design 1, and you have another core that has another design which is completely different. So maybe you cannot even parameterize it to get the second design. So you can change the shape completely. So and you keep using the same model but different configurations, different, for example, core designs. So you have maybe 4 or 5 designs, and you each time you activate one design, do the simulation, whether with EMS or EMWorks2D, then you switch the configuration, the design, change the design, do another simulations, and you compare the results. So you can, for example, investigate several designs, behavior versus or results versus several core designs. Yeah, let me go back. So yeah, in parameterization as well, you can parameterize simulation variables like current and voltages and so on. So it's possible as well. So once, let me create a study, go back here and create a study. For example, let's just use a magnetostatic study. So yeah, a new study is created. So you can see the material list here. So we see the material list. We have the windings and the core. So you can specify the material to the core, for example, using this option, apply material, or you can select from favorite materials, recently applied materials. So if you click apply material, so the material library that came into the software will be opened, And also you can see some materials here. So we have we have a wide list of materials. So you can have like cable, ceramics, conductor, steel. So you can see electrical steel. So two standards here, European and US standards. So you can see that we have a wide range of materials, well organized, linear, some materials that has some linear permeability. So this ferrite, non-linear. So we have another list of non-linear ferromagnetic materials, permanent magnets, and so on. So you can see here other permanent magnets. So several folders with several magnets. And in case you wanna customize material here, so you can add your library, you can edit the existing ones, you can add new materials or whatever you wanna do. So this library can be customized and edited. Also you can add curves. So we have properties like pH curve, PB curve, and so on. So they can be defined in this library. So as you can see some curves here, so you can define your pH curves, your PB curves, maybe conductivity. So in case you are doing some thermal analysis, you can use also some properties that are temperature dependent. So it's feasible as well. So you can import those curves. Also you can create a pH curve here. So it's possible. Let me show you. So automatically you can generate some pH curves. Let me edit one of the materials and say let's suppose that I have permeability. Okay, I'm gonna add a new curve. So pH curve, new curve. So it's here. So you can see this option of generate points. So if you know the saturation and the initial permeability of your material, so you can automatically generate a curve here. It's a smooth curve and contains enough points, so it will ensure good results. Alright, so this is concerning the materials. Once you define the materials, you define your coil. So we have two options, whether solid coil or wound coil. In our case, it's a wound coil, stranded coil. So you specify the coil, entry part actually. So we have one entry part here. For example, I'm gonna choose something randomly. So here, so this option means that the same the exit is the same as entry, since it's cylindrical coil. Then you go to general properties. So here you can see the number of turns, the wire gauge, the diameter, number of turns, and filling factor. So whether you define the wire gauge or the wire diameter or the filling factor, so we have three dependent variables or inputs. So you specify one of them, and both the other variables will be modified automatically. So like let's define, for example, 30. Here you can see that the wire diameter changed, the filling factor changed. So if you know the filling factor, you can directly specify the filling factor. So but if you don't know the filling factor, so you can specify wire diameter. But if you define something non-consistent, so a high, for example, let's say 20, and let me put here something like this, so it will show a warning telling you that the defined wire diameter so led to a filling factor that exceeded the maximum achievable one. So the maximum filling factor should be around 90%. So but here using those data, we got like a filling factor of 1.4. So this is not possible. So this helps the user to put something reasonable, some data, some winding data that are reasonable. Yeah, then you can specify current, your excitation, current, or a voltage. So you can do both of them, one of them I mean. Yeah, so once you define your current, if you want to compute the force, you specify vertical work or Lorentz force. So vertical work is used for ferromagnetic materials. Lorentz force is for conductive materials. Then create mesh and run your analysis. Let me show one of the already solved analysis. So you can see here it is an AC magnetic analysis. Frequency is defined, 50 Hertz. Materials already defined, so you can see some properties of the steel material. Here we can see 6 coils, 6 windings. So we have 3 for primary and 3 for secondary. We have mesh. We created the mesh. We applied the mesh control here. So in this case, the mesh control, mesh control are used to adjust the mesh, whether make it coarse or smaller. So finer mesh. So in this case, we wanted to reduce the computation time, so we applied mesh control that to generate some coarser mesh in the car. Okay, so yeah, this is concerning the setup. Here we have also the windings, the section of the circuit. As you can see, the section of the circuit is here. So we have 6 windings. Each winding has its own coil already defined at the top, the previous section. Winding 1, coil 1, and so on. So we have schematic, and it contains the circuit, our circuit. So here we have short circuit, so we can see the input voltage and so on. The windings, these are the transformer windings and so on. Yeah, if we were using a transient analysis, so we will be able to see more components. Let me switch to transient. So in transient, we should specify the input end time and the time increment. Okay, a new study is gonna be generated. So okay, we need to create a couplet to circuit study. So here transient, couplet to circuit, then say okay. Okay, you can copy everything, every properties that can be copied, and it's the shareable properties that can belong to both studies. So here I'm gonna copy a study AC magnetic to the transient one. So sorry, okay, copy here. So you can see that everything is copied, most of the stuff is copied. So we have the materials, coils, and so on. Now I'm gonna just add windings here, then I'm gonna see my schematic. So you see here, so we have 6 windings. So I'm gonna build my circuit here. So you see here, in addition to the linear components, resistors, inductors, the resistance and the inductor, the capacitance, we have some other components like the diode, switches, and this is the control block for the switches. So this can be especially used in case of wireless application, or wireless power transfer application, transformer, power transformer, electronic transformer, motor application, generators, and so on. Okay, so let me go back here. So you can see so here we have the study structure, we have the tree, we have the mesh, we have the circuit case, and now we can see the results table. So the results table contains the circuit parameters, means the winding parameters, inductance, linkage, flux linkage, impedance, resistance, coupling coefficients, current, voltage, losses, and so on. So it contains several results, so computed by the software. In addition to the results table, we have the 3D plots, magnetic flux plots, and we have field age, current density, loss densities, and so on. So yeah, reports. So reports helps to generate automatically the report, so you can create a report of your work, of your study results, contains the summary about the setup, about the material that was used or were used, and also the results, and so on. Yeah, another type of analysis that we did is the electrothermostructural analysis. As you can see, we have both in addition to the magnetic, we have both coupling, so we have thermal and structural within the same study type. So you don't need to export data from the magnetic simulation to a thermal solver to compute the temperature, then to another structural solver to get the distribution of deformation, and so on. So here, the same structure of the study, you can see the materials here, but in addition to the magnetic properties, we can see thermal properties as well, and mechanical properties. So there is a filter that hides the properties that are not relevant for the study that we are doing. Here we have both coupling, so that's why we can see those or these properties. Here we have three sections of inputs or boundary condition. We have electromagnetic input, it contains coils mainly, and this force and torque definition. Thermal inputs, so it contains the thermal inputs that we can define. So we have convection, temperature, heat flux, volume, heat radiation, and so on. So in addition to the loads that came from the electromagnetic analysis, we can define our own load here. So you can specify temperature, you can specify volume, heat, and so on. So the software will automatically send the losses and so on to the thermal solver, but in addition to that, you can specify your losses. Another section for structural inputs, also it contains some constraints, some loads, force, pressure, moments, and connectors, and so on. Yeah, then once you run the analysis, you will get three results folders. One results folder for magnetic analysis, one for the thermal analysis, results, and another one for the structural results. So we have all the results within the same study, so everything is in front of your eyes. So no need to export or import any data or go from a tool to another to find or compile these results. Yeah, so here you can see just it's hidden. Yeah, some results, so we can see other type of analysis, so we can do so. Yeah, so type of connections and so on. Alright, so this is overall. So this is overall about the 3D. So it's the 2D software is quite similar. So it has the same look and feel. So the same work flow. So it's pretty similar. Just you need to create your 2D model from this 3D one and generate the 2D geometry. Then you go define the setup similar to what we saw in the EMS, and same thing for results folder and so on. Alright, so now let's go back to our presentation, and let's see whether if we have some questions. And yeah, right, thank you. Let's go back to the presentation. Alright, so now back to the presentation, and just before going to the Q&A session, let's conclude our presentation. So yeah, a transformer can cost a lot of money. Then this what makes virtual prototyping and simulation very important. So it can help to save money, effort, and time. So EMWorks proposes a software package that covers both 3D and 2D electromagnetic analysis, and allows a few multiphysics options to compute temperature and structural deformation, for example. So yeah, so force calculation also can be generated. Circuit coupling can be also used to model different type of connections, delta star connections, maybe short circuit loaded with different load types and so on. So dielectric failures can be investigated, so using electric field analysis. Yeah, we mentioned this. So multiphysics behavior can be investigated using both thermal and structural analysis. Alright, thank you for your attention, and let's see if we have some questions. Thank you.